for example, here's another way to explain this. If a language is in the class P, then, and we input a string, there is a deterministic machine here, which gives you a 1 if the string is in the language, and a 0 if it's not, and takes only polynomial time to do that. On the other hand, if a language is in the class NP, there's a non-deterministic machine, which, on the input of a string, will output a 1 if and only if that string is in L, in polynomial time. But in order to do that, the machine has to make all the correct guesses. And that's not actually practical. Cut. This is another way to describe the class NP. If we're considering a particular NP language L, so let's say that L is in the class NP, then there is a way to compute something called the certificate. Now the certificate is polynomial. Suppose that L is the language in the class NP. Then there is a machine which can compute the certificate. If W is a member of L, there is a certificate for W. And then there is a verifier machine which verifies that W is a member of L by using the certificate as evidence. You could think of this as a certificate to practice law or something. To prove that you're a lawyer, you have the certificate which you put into here, and it can be verified. Now, if you have a correct certificate, you can put it into the verifier, and it will produce a 1 in polynomial time. So the verifier works in polynomial time. The generation of the certificate works in exponential time, but polynomial space. And the certificate is generated if W is a member of L. Now you could input an incorrect certificate here, in which case the verifier will say 0. It'll say no. No could be the false answer, of course, because simply you used the wrong certificate. So one way of expressing this, which is in the video that you should have watched so far, the video that's out there on YouTube, which I have a link to, is that if a language is in P, you can decide it in polynomial time. But if the language is in NP, you can verify that a particular string is in the language also in polynomial time. But in order to verify it, you have to have a certificate. Now, in the video that is given on the internet for everybody, they say you have to have the solution and you can verify the solution. And of course, that is a possibility. The certificate could simply be what they call the solution. Like if it's Sudoku, the solution would be the completed table. And if it's a subset sum problem, then the solution would be an appropriate subset. But in more generally, the certificate simply verifies that this string is a member of the language L. Okay. All right, you recall that we talked about reductions. We'll use this notation to say that the language L1 is reduced by a reduction R to a language L2. And if we need to, I'll remind you what that means, but let's not right now. And we're going to say that L1 could be easy or hard, R could be easy or hard, and L2 could be easy or hard. Now, since each of those is binary, there are 8 combinations. But this combination, it's actually the only one that's impossible. If R is easy and L2 is easy, then L1 must be easy. So therefore this line is impossible. All right, now let's look over to here, and we will use a notation here to say that L1 is reduced to L2 in polynomial time, meaning that the reduction, this is a P here, that this reduction function takes polynomial time to execute in terms of the input. And we're saying that this is a polynomial time reduction, and we have this notation. All right, now, here's a definition of NP completeness. This language L2 is NP complete if every NP language can be reduced to L2 in polynomial time. So you can take that as a definition. It's an alternative definition to the other two definitions we have. The first definition was that it can be accepted by a non-deterministic machine in polynomial time. The second definition says that it can be verified in polynomial time deterministically if you have the right certificate for each string. And this one is then the third definition. There's a polynomial time reduction of every NP language to L2. Then L2 is NP complete. All right, now this theorem here is your main theorem that allows you to generate more NP complete languages. So suppose, for example, that L1 is known to be NP complete. This is L2 here. If this was an error here, that's L2. If L1 is known to be NP complete, and you can reduce it in polynomial time to L2, and if L2 is known to be in the class NP, then L2 must be NP complete. And this is an example of how to use this particular fact. We're going to define easy to mean polynomial time. And that could be a function, or that could be a language. And we're going to define hard to mean NP complete. For that would only apply to languages. So if we have that L1 is hard, and then polynomial is easy by my definition, then it is impossible for L2 to be easy because of this fact. And since L2 is not easy, it must be hard, which means it's NP complete in this sense. And so therefore, actually, let me put it a different way. Hard means NP complete, and easy means not NP complete. So actually, I don't need to say that easy means polynomial. Cut.